Alrighty, so let us get started talking about ionizing radiation. My plan is to introduce this subject by talking about basically the fundamental nature of physics, so particle physics, in fact. In order to understand how radiation works, and of course the applications of radiation to medicine, it's helpful to understand the fundamental laws of physics. And what I mean by the fundamental laws is the actual makeup of all the matter in the universe and their interactions. So, radiation, as we will see, is made up either of particles or energy. And energy, in fact, can be thought of as particles itself. So in order to understand how radiation works, how it exists, where it comes from, and what it does, we must understand the interactions of the most fundamental particles of the universe. At least to as good of a job as we can understand them as physicists. So, let me start by discussing what's called the Standard Model. The Standard Model of particle physics is what we call the group of theories, of observations, of particles, of forces, everything we know about how the universe works. This is called the Standard Model of particle physics. It is a theory that physicists have come to agree must be true based on observations and experimentation, that basically describes all of matter and all the forces, all interactions in the universe in terms of particles. So we've already seen, I think you're familiar, at least if you've taken electricity and magnetism, with light. Light is electromagnetic radiation. And when we discuss light in E&M, in advanced physics courses, we generally discuss it as if it's a wave. The wave property of light, how light moves, how it travels, how it interacts. A lot of times we think of it as a wave. However, as you see in quantum mechanics, light also has a particle nature to it. And as quantum mechanics was built up, it was discovered that everything we know of, has some wave-like nature and some particle-like nature. That is to say, depending on what kind of experiments you do, you might discover that this, whatever thing you're looking at or you're investigating, acts like a wave, or it has wave properties. Or if you do another experiment to look for something else, you might discover that that same thing you were investigating now acts more like a particle rather than a wave. And quantum mechanics, as a theory, helps us to come to grips with this and to just allow for the fact that all of matter, and as particle physics will describe as well, all the forces can be thought of as some new thing that is neither particle nor wave, but some new thing that has characteristics of both. And so, the particle physics, the Standard Model, is a very, very nice theory. It describes all the particles we've ever seen in experiments, every particle we've ever observed. It also includes all the particles that were ever theorized that must be true based on mathematical theories and physical theories. And those theories have been verified through experiments. In fact, the latest one was the Higgs boson, which was found over at CERN, particle accelerator, not too long ago. So what is the Standard Model? Well, as I said, it breaks everything down into particles. So all of matter is particles, and in fact, forces can be thought of as particles too, which we'll try to see how that works. So if we try to do this, first thing we need to do is break everything up into two different things. They are either fermions or bosons. Everything in the universe that we know to be true, to be real, that we've observed, fall into one of these two categories, fermions or bosons. And they're called this because the fermions obey what's called Fermi-Dirac statistics, which basically is a mathematical way of describing how they interact, whereas bosons obey Bose-Einstein statistics. And the biggest difference between these two is fermions. You cannot have more than one fermion in the same quantum state. One fermion per quantum state. And what that means is you can't have, for instance, two electrons in the same place at the same time. They can't be in exactly the same location. If they have all the same spin, they have the same charge, then you can't have one electron right exactly where another one is. Obviously, I mean, you can't have, for instance, two baseballs, one inside of the other. If there's a baseball somewhere, you can't put another baseball in that exact same space. It has to go somewhere else because there's already a baseball there. However, with bosons, this isn't true. You can have an infinite number in the same quantum state. And so, an example of this is light. Particles of light called photons, we'll discuss. You can have as many photons in exactly the same place at exactly the same time, and it's perfectly fine. And so these are the two big classifications, fermions and bosons. Now, we can further split these classifications up. The big thing here is fermions have half-spin particles. This is something you learn in quantum mechanics. And bosons are integer spin particles. So spin 1, spin 0, spin 2, things like this. That's basically the difference at the fundamental level. All particles have spin or spin 0. And if the spin is 1/2 or 3/2 or 5/2, some half integer spin, then they're fermions. If the particle has integer spin, like it has spin 1 or spin 2, then it must be a boson. All right, now let's look at the fermions. The fermions have their own set of classifications for their particles, which are the leptons, the mesons, and the baryons. Now, the mesons and the baryons together are called hadrons. So, the particle accelerator at CERN, called the LHC, is called the Large Hadron Collider because the things that it collides together in doing their particle collision experiments are either baryons or mesons, depending on what experiment they're running. It could be protons, it could be LHC. The H part is hadrons, and hadrons are the classification of mesons and baryons together. Now, what are these? Two of these classifications you're familiar with. For instance, leptons, the one you're most familiar with, is called the electron. The electron is the famous, most familiar lepton. Lepton means light particle, light meaning not heavy. Okay, not like electromagnetic radiation light. This light is like it's not heavy. They're very light particles. Baryons, these are things like protons and neutrons. And baryons means heavy particles. Mesons are kind of in the middle, medium. Meson is like medium particles. And these are things you may not be very familiar with, but they're things like the pion and other particles, which we don't have to get too much into for now. But, there's a lot more particles, hundreds and hundreds of particles out there, and they're classified into one of these sets, or bosons. Now, this isn't everything. As I just said, leptons, there's more than just the electron. There's something else you need to know, which is called the neutrino. The neutrino is an interesting particle. It was theorized, but wasn't observed for a very, very long time. And that's pretty easy because neutrinos can only interact by a very special way. You can't shine light on them. They're extremely light particles. In fact, for the longest time, it was thought that they had no mass whatsoever, and so you couldn't feel them by gravity. And so there was only a very specific way to ever interact with neutrinos. So for a long time, the theoretical physicists knew they must exist because of their calculations, but it was a long time for experiments to show that they do indeed exist. Well, it turns out that there's more leptons than this. In fact, leptons come in 3 different families. There's the electron family, which is the electron and the electron neutrino. Then there's the muon and the muon neutrino. And then there's the tau and the tau neutrino. So what are these? The muon is just like an electron. It acts the same way, except it's heavier. It's got more mass. And because it's got more mass, it's not very stable. So when a muon is produced, it interacts. Let's say you have an atom, for instance. Well, you can have a muon circling the nucleus, just like electrons circle the nucleus. It would do exactly the same thing, except because it's heavy, it doesn't want to exist. So it breaks apart into electrons and other things. So and tau is the same, only it's even heavier. So the electron is the one we know because it's the lightest version. So it's the one that sticks around. It's stable. But there are 3 families. There's the electron, the muon, and the tau. They're all leptons. They all act kind of the same way. It's just that a muon is heavier than an electron and a tau is heavier than a muon. And a muon and a tau, because they're heavier, are unstable and thus decay and break up into electrons. Now the baryons, I say, there are protons and neutrons. But there are more, of course. And in fact, trying to Think of, for instance, there are things called like the delta and the lambda, the omega. I mean, there's a whole bunch of these particles. The ones we know, of course, are protons and neutrons, and that's because all the other ones that exist are really heavy, and so they're not stable either, and so they decay down to some combination of protons and neutrons and other things, of course. Now, it turns out that when we want to discuss baryons, the proton and a neutron, it's actually not true to think of the proton and the neutron as fundamental particles. For instance, we think of the electron as a fundamental particle. That is to say, the electron never breaks up into pieces. If you have an electron, no matter what you do, it'll always be an electron. It'll never decay to something else because it's the lightest version of itself. And when we try to look at it, the way particle physicists look at things is if it's big enough, they shine light on it. And of course, in order to shine light on something very small, that light has to be very, very high energy. Because as you learn in electricity and magnetism and modern physics, in order to see something with light, the wavelength of light has to be smaller than the particle. You know, if you've got a particle this size, and you got a wave this size, well, the wave just goes right through. It doesn't really see it. However, if the wave is this big, the particle's bigger, then that light can reflect off of it and we can see it. So, in order to see something extremely small like an electron, we have to have light that's extremely high energy, very, very small wavelength. And generally speaking, if there's anything inside of it, we hit it with such a high energy light that it'll break apart into its pieces. We don't see that ever happen. Another thing particle physicists do is they shoot other particles at them. In fact, that's what the CERN does. Any particle accelerator you see takes a particle. We want to see what is this particle made of. We take another particle and we hit it as hard as we can. And what does it do? It breaks it up into pieces. And we study the pieces. And that tells us what the original particle must have been made of. The simplified view, but that's basically what they do. The classic example is... you know, if you want to study how a clock works, you take a clock, you hit it with a hammer, and then you study all the pieces that break off of it and try to figure out how the clock worked to begin with. It's hard to do, but we can do it. So with electrons, we do this kind of stuff, and we never see anything inside of the electron. The electron is what it is. It's not made of anything. It's its own particle. So it's fundamental. And so we did the same with protons. We took a proton and we said, is it made of anything? Or is it its own fundamental particle? And same with a neutron. And it turns out when we did experiments, they are not fundamental particles. In fact, the proton and a neutron are both composed of other things. In fact, those other things are called quarks. What we found is that a proton, let's say this is a proton, is made of 3 quarks. Here's one, here's one, here's one. And a neutron. If we have a neutron, it's also made of 3 quarks. Now, we try to figure out what, are they the same quarks? Is it, obviously, if the proton's made of 3 and a neutron's made of 3, the quark itself can't be just a quark, because why is a proton different than a neutron? If they both have 3 of these things, yet they're 2 different particles, then it must be true that the things they're made of must be different too. So it turns out that the quarks inside of a proton are not necessarily the same as the quarks inside of a neutron. And what was found is that proton is made of two quarks that are the same type. We'll call it U and U. And another one which is different called a D. And a neutron, when we look at it, it's made of two Ds and a U. So they're made of the same quarks, U's and D's, but in different ways. The proton has two U's, whereas the neutron only has one U, and vice versa with the D's. So now we know protons and neutrons are not fundamental particles. So when we try to do things in particle physics, we don't like particles that are not fundamental. We want the fundamental stuff. So we don't talk about protons and neutrons, generally speaking. What we talk about are quarks, because the quarks are the fundamental particles. So we'll talk about quarks. Quarks are those things which make up the hadrons. Every hadron, so that's baryons and mesons, every hadron is composed of some number of quarks. Baryons have 3 quarks, whereas mesons have 2. And in fact, it's 1 quark and 1 what's called anti-quark. It's like the antimatter version of a quark. Okay, so that's why baryons and mesons are not classified as the same thing. Baryons have 3 quarks. Mesons have a quark and an anti-quark. So they're composed differently, so they're in 2 different classifications. So every proton always has 2 U's and a D, and every neutron has 2 D's and a U. Every single one. Now, as we talk about quarks, we want to know more about them. Where do these letters U and D come from? Turns out that we call them, for no reason other than to give them names, up quark and down quark. Okay? Now, there's nothing up and down about it. They're just arbitrary names. But, of course, in quantum mechanics, we talk about spin, and things can have spin up and spin down. So up and down are good names, just taken kind of like from quantum mechanics. What do we know about these quarks? Turns out that every up quark has a charge of positive 2/3, the charge of an electron. Okay? So we used to think that the fundamental charge in the universe is the charge of an electron, or proton, of course, they have the same charge, because we never saw anything that doesn't come in an integer multiple of that charge. It's either 0, 1 charge of an electron, 2 times the charge of an electron, 18 times the charge of an electron. It's always multiples of that number. However, now we know these particles exist, and they're not multiples, they're fractional. The charge of a down quark is -1/3 the charge of an electron. And we could see if this works. We know a proton has a charge of +1 Q. We know it has 2 ups and a down, so that means it's got 2/3 plus 2/3 plus -1/3. If we add all 3 of these together, we better get +1. Well, 2/3 plus 2/3 is 4/3, minus 1/3 is 3/3, which indeed is +1. So that works mathematically. And we could check the same for neutrons. Neutron has a charge of 0. So let's see. Down, down, and up. That's -1/3 plus -1/3 plus 2/3. -1/3 plus -1/3 is -2/3 plus 2/3 is in fact 0. So the math works. So now we know there are 2 quarks out there. When you combine the quarks in certain ways, you get different particles. So if you have two ups and a down, you get a proton. You get two downs and an up, you get a neutron. If you have three downs, you get something else. If you have three ups, you get something else. That's some of those other particles like lambda and whatnot that I talked about before, but we don't see them generally. These are the two we see, protons and neutrons. Well, we studied this for a long time and found that, like the electrons, quarks come in other families as well. So not only are there up and down quarks, there's another set, which is called, it's kind of weird, but the first one is called charmed. And the fourth one is called strange. Very strange names for these things, but again, they're just names. It doesn't mean anything at all. They're just kind of labels to place on these things. And it turns out that the charmed quark is just like the up quark, except heavier. It's exactly the same in every way. Same spin, same charge, everything. It works just like the up quark works. And of course, the strange works just like the down quark. Same charge, same spin, everything's the same, except it's heavier than the down. So because the charm and the strange are heavier, they're not stable. Particles that are created with these decay and break up into pieces, eventually leading to protons and neutrons. Which is why anytime you look in the universe, you always see protons and neutrons. You never see any of these other particles naturally. Well, it turns out there's another family past that one, and it's called top and bottom. So we have U, D, C, S, T, and B. And that's it. There are no other families other than these three. So like the electrons, like the leptons, I should say, where we have three families, electron family, the muon family, and the tau family, quarks have the same relationship. There's the up and a down. The charm and the strange is like up and down, but heavier. And then top and bottom is like up and down, but very, very heavy. So those are all the quarks that make up everything we know of. Anything that's made of these bottom four quarks always breaks down into some combination of the top two. Now, unfortunately, that's not the whole story. Turns out that not only are there three families of quarks, there's also what's called three colors. So now, please don't think that they're literal colors. They're not really colors. They're labels that we've placed on them. But instead of calling them, quark A, quark B, and quark C, which is boring, we call them red, blue, and green. So every single quark can come in one of three colors. So you can have an up quark that's red, or an up quark that's blue, or an up quark that's green. When we try to study it, we don't see any difference whatsoever between a red quark and a blue quark other than this characteristic, this label we call color. They're not heavier than each other. Their charge is identical. Some protons have red quarks, some protons have blue quarks. I mean, it's just completely, it's as if it's a characteristic which exists but has no purpose, at least as far as we can tell right now. The only thing we know about these colors is that when you have three quarks put together, like up, up, and down for a proton, each quark has to be a different color. So this is what's called quantum chromodynamics. Quantum chromodynamics is the field of study of this color characteristic. And the rule we have found to be true and is always maintained is that when you have a particle created of quarks, the particle must be a total color of white or black. And what I mean by that is if you have one of these baryons, one of these hadrons, I should say, one of these baryons, let's say proton or neutron, then the three quarks must be a red, a blue, and a green. Now, it doesn't matter which is red, which is blue, and which is green. So you can have, for instance, a proton, which is a red up, a blue up, and a green down. Let me do it this way. You can have a red up, blue up, and a green down. That's a proton. You have another one, which is a blue up, a green up, and a red down. That's also a proton, and there's no difference between them. We have no way of telling the difference between these two protons. They're identical in every way. But it must be that you have a red, a blue, and a green. Which is which doesn't matter at all. For the mesons, which I already said is, for instance, an up and an anti-up, well, for that, you must have a red up and a red and an anti-red. Look at this. Too many lines. A red up and then an anti-red up. And so this is called black because you have the color and its opposite. It's like they cancel out. Whereas this one is called white because it's got all the colors together, which makes up white. And that's what quantum chromodynamics is. This is a field of study, very complicated. But the basic rule is when you create a particle out of quarks, you must always create the particle either to be white or black. Now again, these aren't actual colors. You're not going to look at it in a microscope and see that this thing is red or blue. They're labels, but they're made colors because of this combination thing. It makes it easier for us to understand. So that's how quarks work. Quarks come in three families: the up-down, charm-strange, top-bottom. And for every one of those, there's a red, a blue, and a green version. If you have three quarks together, that creates a baryon. If you have a quark and an anti-quark, that's two quarks together, but one is anti. That's a meson. They follow quantum chromodynamics rules for combining, which is baryons have a red, a blue, and a green quark. Mesons have a color and anti-color quark. All right, so that's all I want to say about the fermions. What about bosons? That's the other classification from the very beginning that I didn't discuss. So all of these I've talked about so far are fermions. Bosons is the classification which includes all of the forces. So you can think of fermions as like the matter particles, all the particles that produce matter. And you can think of bosons as all the particles that give rise to forces. It turns out that in this universe, every single interaction you can ever think of is one of four different forces. There's gravity. There's electromagnetism. And there's two other forces which are not quite as well known. The first is called the strong nuclear force. And the last force is called the weak nuclear force. And every single interaction you can ever think of in this universe, planets orbiting each other, you sitting in your chair and not falling through, radiation, everything you can think of is one of these four forces. And it turns out that each one of these forces has its own particle. When we do particle physics, everything is a particle. And so gravity is the graviton. That's the particle of gravity. It's called the graviton. Electromagnetism is the photon. That's light. The strong nuclear force is something called the gluon, which is a funny name because what it does, the strong nuclear force, holds the nucleus together. It holds quarks together. So it's like a glue. It holds the things together when they don't want to be. And in a future video, I'll show you why the strong force is so important. And the weak nuclear force, which is what is the cause of one type of radiation, are what's called the W and the Z bosons. Not as nice of names. One is called the W. There's three here. There's the W and the Z. One's positive, one's negative. That's why there's three. And so our four forces in this universe, there are particle versions of them. And these are their names. And so these are the bosons. Of course, now we know there's also the Higgs boson, which doesn't really go with a force per se, but it is the thing which gives rise to the mass of the particles. So that's another boson which now exists, which we've now seen experimentally, but was theorized, in the 60s. All right, so for now, that's all I want to say about the Standard Model thus far, but this is everything we know. We know there are fermions and bosons. Okay, the fermions are like matter particles, things like protons, neutrons, and electrons. Bosons are forces. Fermions come in three different types, two big classifications. One is the leptons, which are the things like the electrons and the neutrinos, and the other classifications are the hadrons. The hadrons are broken up into two things: mesons, which is quark and antiquark, and baryons, which are particles which have three quarks in them. We know the quarks themselves, because protons and neutrons and these particles are not fundamental, they're made of quarks. The quarks come in three families: up, down, charm, strange, top, bottom. What we see in our everyday lives, and pretty much any time we look out into space, we see just ups and downs. That's all we see. The only time we see any of the other ones are when we have extremely high energy stuff going on. So we look in the sun. We look at high energy collisions from outer space hitting our atmosphere. There's enough energy there to produce these other types of quarks. When we do experiments in the lab, we could produce these types of quarks. But they don't exist naturally because they're unstable, being so heavy, that they naturally decay almost instantaneously after they're created into the ups and downs. We also know that for every one of these quarks, there's a red, a blue, and a green version, which they all act identical, but they just have this label. And the rule is when you put three quarks together, you must create a white particle, which is a red, a blue, and a green quark. Which is which doesn't matter as long as there's at least one red, one blue, and green. And of course with mesons, you take the color and its anti-color to make a black particle. Finally, the bosons, the forces. This is the four fundamental forces of the universe: gravity, electromagnetism, strong force, and weak force. Each one has its own particle associated with it. And what I mean by this is, if you have two electrons, they repel. We know they repel because they're like charges, and we know like charges repel. But we can ask the question, how do they repel? They don't see each other. They don't have eyes. They don't know, hey, look, there's an electron sitting there. I better move away. They don't touch each other, so it's not like they hit each other and bounce. So how do they know to repel? Well, it turns out that what happens is one sends a photon to the other. That's why the photon is the particle for the electromagnetic force. The other one grabs it and is pushed away. He then sends another photon back. He grabs it and is pushed away because of conservation of momentum. That's a very, very simplistic version of what happens, but it's a good way of thinking about it. You know, if you have two people on ice skates, one person throws a heavy school bag towards the other person. The person that threw the school bag moves backwards. The person that catches the school bag also moves backwards. So it's like they repelled each other. Same thing here. The thing they're throwing towards each other are photons, the particles of the electromagnetic interaction. And the same can be said for gravity, a strong force and a weak force, with their particles instead. Now next time, I want to get into a little bit more of the nuclear physics part of things. This is particle physics. This is most fundamental level. We're going to move up a level, a little more general, from particle physics to nuclear physics. What are the nuclei made of? How do they hold together? And when do they not hold together? When are they radioactive? When do they break apart and decay into radiation? Once we understand that, we'll do some calculations and we could get started in some experiments for how radiation works. So for now, I hope this is understandable. I hope this gives you some look into kind of the format of how we think about the universe in terms of particle physics, how things are arranged, what is everything made of, and how we could think about everything. And that way, in the future, when we start discussing names of things and topics, it's a little more understandable where these things are coming from. So until next time.